So, hello and welcome again to the lecture course on relativity and cosmology. We are doing gravitational waves, and last time you have seen the derivation of this very important and central formula derived for the first time by Albert Einstein in 1918. It's the quadrupole formula. So you have the quadrupole tensor of a source, say two stars rotating around each other. And the left-hand side is the emitted power, so energy per time or luminosity. And you see it's the third derivative of the quadrupole tensor that enters. So if you go to Fourier space, because of the two triple derivatives, you have an omega to the 6 in Fourier space, so frequency to the 6. There's no dipole radiation here, as I have explained. Now, what I do right now is to calculate the metric perturbation, well, the rescaled metric perturbation phi, for a simple example. And we had derived here this expression, which is also related to the second time derivative of the quadrupole tensor, and we would like to calculate this for two stars rotating around each other on a circular orbit, and with equal masses. Okay, when they have equal masses, they rotate on a circle. And I will give you the generalization later, but all the interesting things can be seen already here. So for the star 1, I have x1 of t is r cosine omega t, so capital R is the radius here of this orbit, and y I1 of t is r sine omega t, and it's in the xy plane, so z1 of t is 0, and of course this also holds for the second. And the second star has just here minus signs. So I will not write, okay, maybe I can x2 of t is minus r cosine omega t, and similarly y2. So what we have to do is to calculate the quadrupole tensor. So q ij is m times xi xj 1 plus xi xj 2 minus 1/3 delta ij x1 squared plus x2 squared. Now for this particular example here, this here is constant. I mean, this x vector is x1 squared plus y1 squared. So this cosine squared plus sine squared is 1. So this is constant. That is, this term does not enter in the calculation of the derivatives of the quadrupole tensor. So I will not actually need to calculate it, because we need only the time-dependent part. So this here, these are time independent expressions, so will not enter qij double dot, and in fact then this is then already the qij double dot here. I mean, this will not enter. Now the calculation of this is simple, so let us have a look at q11. So inserting these expressions here, so I get for q11, which is the qxx, r squared cosine omega t from the first star, and from the second star we have a minus r cosine squared, so this gives the same expression. So this is r squared minus cosine omega t squared, and we have this part which will not enter. So, and you you find then for this it's 2m r squared cosine squared omega t, which you can minus neglected terms, and this is m r squared 1 plus cosine 2 omega t minus. So you see here twice the frequency enters, and this will be important. Now for Q22, then these are the y components, and the calculation is similar to that, and we get m r squared 1 minus. You get a sine squared, and you can also write it in terms of the cosine 2 omega t, and it's 1 minus cosine 2 omega t minus, and so on. And for the mixed term, you get here terms cosine times sine, and that's 2m r squared sine omega t cosine omega t, which you can write as m r squared sine 2 omega t. So you see, for such a simple case, but a prototype example, the quadrupole tensor is easily calculated. So we have to insert this here into the expression for phi ij, and I can write it as a 3 times 3 matrix just using this. I mean, I will not write down the calculation. I mean, you have to calculate the second time derivative of cosine and sine, and that's a simple exercise which I will not repeat here, but you will then get from this that phi ij of x and t for r to infinity, so far away from the sources, is then minus 4 omega squared g m r squared over small r, and then you have the following expression, cosine 2 omega of t minus r. No, so here recall that this has to be evaluated at retarded time. This is why I have here in the argument not t, but t minus r. This has to be evaluated at retarded time. Sine 2 omega t minus r and 0, and sine of 2 omega t minus r minus cosine 2 omega t minus r, 0, 0, 0, 0. So that's the important result. So you see here we have the occurrence of twice the angular frequency of the motion. So the emitted wave has twice the frequency of the orbital motion. Now that's important. So frequency of the emitted radiation is twice the orbital frequency. Now you also see here the 1 over r, which is already here, which is typical for the radiation field. So the amplitude decreases away from the source linearly with the distance. And I mentioned already earlier that typical value of this, of course, you must insert parameters of stars and black holes and so on. But typically this is of order 10 to the minus 21, which makes it very difficult to observe it directly. We will come to this in the next section. But I should say, so typical amplitude is of the order 10 to the minus 21. Which is challenging. Let me give a brief example of, say, what you get for the frequency, say, for a star, for a binary star. If we take this amplitude here, I mean, we have here minus 4 omega squared gm r squared over r. Then if we insert here the period of the binary star here, capital T, which is directly observable, and then this gives minus 16 pi squared over t squared gm over r, and then we have r squared. Now, you know, Kepler's third law gives you the relation between the r and the orbital period. So if we insert this, we had this earlier also already, r squared is gm t squared over 16 pi squared to the 2/3. Then you get, I mean, from this here, so this is then equal to a prefactor minus 16 pi squared to the 1/3, which is around 5, and then you have gm over r and gm over t to the 2/3. So that would be, I mean, from a binary star in the distance small r, the amplitude of the gravitational waves in terms of the masses of the two, which are here equal, and the observed period. So one example that I took from the literature is a binary star in the constellation Boötes. So Iota Boötes, a star, binary star. There we observe that t is approximately 6.5 hours to circle around each other, and the frequency from the period is nu, okay, is twice times omega over 2 pi, which is then, okay, twice omega, but we have here the ordinary frequency, this is the angular frequency, so it's just 2 over t, and the numbers give you around 9 times 10 to the 5 hertz. Yeah. So having done this calculation and setting in values from astronomical tables, you can estimate what amplitude you get, what frequency you get, and so on. Now here you get 10 to the minus 5 hertz. That's, as I will tell you in the last section, that's too small to be observed here on Earth because of seismic perturbations that we have here. So we cannot observe frequencies below, say, roughly 1 hertz. So this you could only observe from future missions that are in space, where you can observe very small frequencies. Let me also now, for that case here, and I think it will fit here, from the quadrupole formula, the emitted power. So if you insert here those values into that, I mean, you have then to perform the third derivative, so one more derivative. Then for the amplitude, you get that minus dE over dt is, okay, if I set c equals to 1, then it's this expression. And the result of the calculation, which is a bit lengthy but not much, you just have to play around with sine and cosine, it gives me 128 over 5 g m squared r to the 4, and of course this omega to the 6 factor. If you plug in numbers, say astronomically motivated numbers, then this is around 1.9 times 10 to the 33. If you measure m in solar masses and the period in hours, then to the 10^3 erg per second. No? The Gaussian units, the watt is a factor of 10 to the 7, different from that. So that would be, say, an estimate that what you would expect given such a situation with two masses small m orbiting around each other with period t. Now if you compare this, say, well, this has the factor 10 to the 33, so this is typically of order 1. So you expect this luminosity. If you compare this with the solar luminosity, I mean in electromagnetic radiation, then you know from astronomy this is roughly 3.9 times 10 to the 33 erg per second. So you see these numbers, they are not so different. So the emitted power here, the luminosity and gravitational waves of these two stars is comparable to, say, to the luminosity of a star like the Sun in electromagnetic radiation. So at first glance you would perhaps be optimistic to say, well, then we can easily detect that, but unfortunately this is not true. The detection of gravitational waves is much more difficult because of the tiny coupling that you have to the detectors. And this is why, in spite of the enormous luminosity that is emitted, the detection is difficult. Let me here mention one final thing here. So you see that this expression is already in transverse traceless form. So it corresponds to the emission in z direction, which is here orthogonal to us. So it has can be written as a sum of this diagonal term, cosine and minus cosine, and the off-diagonal term. So we have seen earlier that these two corresponded to the two independent linearized polarization state, the cross polarization and the plus polarization. So this is actually a superposition of the two, which gives you a circular polarized state. So you see here, by going to the z direction, this is already in, because this here is the z direction here, this is already in the appropriate form. And we conclude that we observe a circular polarized state. Now what about the other direction, say the x direction? Now if you have the x direction, then with respect to x, this is not yet in transverse traceless form, but you can transform it into such by matrix operations. But what you find then is that it's no longer a circular polarized state, but this is what you find in this case, a linearized polarization state, linear polarization state. So this means that actually the polarization depends on the direction of observation, which is maybe not surprising, but it's important to note. And because we have only in x direction one linear polarization state, of course the energy flux is only half of this, because this is a superposition of two polarization states, two linear polarization state, and so the energy flux of this is twice, say, of this in the x direction. So I make this remark here that polarization and flux are angle dependent. So this you have to take into account when you're an observer, that it depends on the angle that you have with respect to the motion. So far we have treated the example of two equal masses. If we have two unequal masses moving first on a circle, then we get the following result for the emitted luminosity. We had this earlier for the case that one mass is much smaller than the other one. If this approximation is not applicable, if they are arbitrary, you get rather straightforwardly this formula, and we have this symmetric expression in the two masses. Now, in general, of course, stars move around each other on ellipses, so the circular case is a very particular one, so you have to generalize the whole calculation with the quadrupole formula to ellipses. This in fact has been done long ago, and I just cite the result. So if you have a generalization to elliptical orbits, this was done by Peters in 1964, and you get then a modification of that formula which contains the numerical eccentricity of the ellipse in addition. So what you get is here LGW is minus 32 G to the 4 over 5 C to the 5, and then we have M squared M plus M small m squared. So A is the major half axis of the ellipse, and then we have 1 minus epsilon squared to the 7/2 and 1 plus some strange fractions epsilon to the 4. No? So this looks like an expansion, but it's not. That's the exact result. And of course this is an important formula because this is what you have to apply for the realistic case. I mean, the numerical eccentricity, of course, you know from your elementary geometry. So this is square root of a squared minus b squared. So this is the minor half axis over a. So this is the numerical eccentricity of the ellipse. I just cite this formula because it's important, not because we need it. The emission of gravitational wave leads to a decrease of energy because energy is emitted. We have power. This also leads to a decrease of angular momentum. And I mentioned the formula. So emission. So this is a general formula. Emission of gravitational waves also leads to a decrease of angular momentum, and the result, which I only quote here, is dLi over dt. So Li, this denotes the spatial components of the orbital momentum of the binary system, or whatever system. Is a general formula, is minus 2g over 5 c to the 5 epsilon I jk q jl triple dot q kl double dot. Now, so here there is, in the second q, there's only a second time derivative. So angular momentum decreases, but also the eccentricity of the orbit changes according to the following law. We have the relation of epsilon with the energy, angular momentum squared, and the gravitational constant, m plus m over m q. So the form of the orbit changes too. Now let us go to one important example, namely to the binary pulsar. Binary pulsars are objects, I mean binary stars if you like, where you have two very compact objects, one of which is visible because it emits flashes of light. These are the pulsars, or flashes of radiation. And the other, the companion, can be a neutron star or a black hole, but you cannot directly observe it. These days there are very few examples of so-called double pulsars, where you can see both, but the general case is where you can only see one. And this was important for the history of detection of gravitational waves, because indirectly this formula could be tested. So effects of gravitational radiation detected in a binary pulsar. So the emission of gravitational waves will of course reduce the energy, the angular momentum, and if we recall the Newtonian expression for the major half axis, then I just cite this. We have this formula where of course the energy is negative, and so you see from this, if E dot is negative, then we have A dot is negative, and from this we have T dot is negative from Kepler's third law. So what you see here in the major half axis decreases, and also the orbital period decreases, and this you can directly observe. Let us, just for the sake of the presentation, go again to our example with the circular orbit and with having two masses of equal size here, then oppositely moving around each other, and the radius of that circle is r. We can get then here the energy directly from the virial theorem, because the averages correspond to the quantities themselves. So this is kinetic energy plus potential energy, and from the virial theorem we know that this is minus v over 2. So this is v over 2, and this is minus g m squared over 2 times 2r, no? Because the distance is 2r between the masses. So if we again use Kepler's third law, we have r is gm t squared over 16 pi squared to the 1/3. Then we have here minus m to the 4 times 4 pi gm over t to the 2/3. And if we use the emitted power, so we have E dot, which is the same as the luminosity that we have written down here. So you have this, take this formula by taking small m is equal to capital M, and you get this minus 64 g to the 4th over 5 c to the 5, and you have m over 2r to the 5th power. Yeah, and then from this here, here you have E as a function of the period. So you can relate E dot to T dot. No? So from this you find that the T dot, when you calculate T dot here, then it gives you E dot, and you insert the E dot here. So from this you get the T dot is a minus 96 over 5 c to the 5 pi times 4 to the 1/3 times 2 pi gm over t to the 5/3. And if you introduce here again typical astronomical values, so you measure this in solar masses and the period in hours, then you can write this as minus 3.4 times 10 to the minus 12, and then you have m over solar masses and 1 hour over t to the 5/3. So that's then here the result that we have for two equal masses and for circular orbit. So you see this is dimensionless, no? It gives the time derivative of a period. So it gives you the rate of the shrinking of the orbits. And you see it has this order of 10 to the minus 12. Now there is one famous binary pulsar, PSR 1913 plus 16. So this refers to the coordinates of this object in the sky, and this was discovered in the 70s by Hulse and Taylor, 1974, and the values, the parameters of that first mass is 1.44, the heavier mass 44 solar masses, and the second mass is around 1.39 solar masses, and the time, the period is around 7 0.75 hours. So you see this is justified. I mean, it's the order of hours, and this is of the order of the solar masses. And actually you see they're rather close together. So this approximation with equal masses is actually not too bad to get this. But of course you must then insert the full elliptical formula that we have here. Hulse and Taylor received for this the Nobel Prize in 1993, so roughly 20 years later than the discovery. And I cite from the Nobel Committee, they got this for the discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation. And one of these possibilities is the indirect observation of gravitational wave emission, because as I will write down for you, this T dot has actually been observed over time. So if you take into account this exact formula, then what you get is the T dot over T is minus 96 over 5 c to the 5 m, and you get T over 2 pi to the 8/3 m plus m to the 1/3, and then you have a function of the eccentricity, which is coming from this here, and this function of the eccentricity is 1 plus 32 over 24 epsilon squared plus 32 over 96 epsilon to the 4th, and you have 1 minus epsilon squared to the minus 1/2. And from this, if you insert the parameters of the binary pulsar, which are the two masses and the period, and because they are really two compact objects, and this is a very clean two-body problem, much easier than in the solar system where you have many planets and they perturb. You have just two bodies, so you have a very clear two-body problem, and one can observe very precisely the small m, the capital M, and the T. So what you get from this is that the T dot, the predicted T dot for the binary pulsar, is minus 2.40243 plus or minus 0.00005 times 10 to the minus 12. So this theoretical uncertainty comes not from the uncertainty in doing calculations, but from the uncertainties in the parameters that you put in. And it was found out that this agrees with the observed value at the level of about 0.5%. So agrees with the observational value to about 0.5%. And this has been seen by observing this binary pulsar over many years, since 1974. And what you get from the observation, so this started in 1974, and it's still going on, but at least up to, say, 2010 or so, you can observe the change in the period of the pulsars orbiting around each other. And what you find is you have here the prediction from Einstein's formula, and the observed values, they lie within the error, in this position on that curve. So that's an extremely valid observation, and this is of course contributed to the dedication of the Nobel Prize to the two discoverers of that binary pulsar. So gravitational waves have been observed to exist indirectly already decades ago. Yeah, when it's ongoing, but I could write decades ago, because as we shall see, the direct detection is not that old. One small remark, of course, we have used here for this linearized gravity, so having small perturbations, and also that the matter moves non-relativistically. We have this ellipses and Kepler's third law and so on. This can be justified in detail for most of the evolution of this double pulsar, so they will of course speed up when circular to each other, and when they come very close to each other, the motion becomes relativistic, and also the linearized approximation breaks down. But this will, concerning the time, only be the last fraction of a second of that motion. So that is not relevant for these observations, but it's relevant, of course, for what we shall discuss in a minute when we have the direct detection of the final merger. Of course, for that final merger, only numerical analysis can be done, because you have to use really the full Einstein equations with their full nonlinearity. So we now come to the last section of the chapter on gravitational waves. So we had propagation, emission, and of course the last thing is detection. You have learned in the previous section that there was already an indirect detection in the sense of an observation by from the orbital decrease of orbit of binary pulsars. But of course we would also like to detect this on Earth, and this has been accomplished. So let me briefly review this without going into much detail. So the oldest detectors, so the first detectors, were so-called resonance bars, also called Weber cylinders. Because the American physicist Weber observed or built them and wanted to observe gravitational waves from the 1960 on. So from around 1960 on. And so the idea is simple. You have a resonator in the form of a cylinder. So if the wave comes, I mean, it will change the distances transversal to the direction of the wave, and so it will have an effect on that cylinder, like if you hit a bell, and then you will have typical oscillations. So the typical value of this was, okay, you had a cylinder from aluminium with lengths of around 3 meters and a mass of around 1 ton. And have a resonance frequency, and this is of course only the only frequency range where you can measure something, which is in the range 500 Hertz to 1.5 kilohertz. Now I have told you that a typical amplitude is 10 to the minus 21 of an arriving wave. So if we have a gravitational wave with amplitude of 10 to the minus 1, so you get a relative change in distance of the order of a amplitude times the original length, which is the order of 10 to the minus 21 meters. So this is impressively small. So this is much smaller than nuclear radii, which means that you cannot immediately observe this. No, so this is the regime of quantum mechanics, of quantum optics. So if you compare this, say, with the ground state of a harmonic oscillator, with, say, frequency of 1 kilohertz, which is in this regime, well, then, I mean, taking your quantum mechanics notes, you find this expression. It's square root of h bar over 2 pi mf, and if you insert f and the mass here, then you find that this is around 4 times 10 to the minus 21 meters. So you see this is of the same order of magnitude. So this here corresponds to the ground state uncertainty, if you like, of a harmonic oscillator. So to get any information on gravitational waves, of course, you have to do quantum optics. Well, up to now, these resonance bars, and there still exist some, have a sensitivity of 10 to the minus 19, so they are not yet really able to measure these small amplitudes. But maybe new technologies, of course, you have a cooling below 100, say, millikelvin, could bring this to that level over a bandwidth of around 100 hertz, which is, of course, a bit big disadvantage, because the resonators, they are only sensitive at a particular frequency. So the wave that comes must have just the right frequency so that the bar oscillates with the resonance frequency. So far, no one has seen gravitational waves with resonance bars. Actually, Joe Weber concluded in the end of the 1960s, beginning of 1970s, to have observed something, but these observations have never been confirmed by other groups who did that. So it's not clear what kind of effects he saw, but there is in the community no doubt that these were not gravitational waves. Now, because of the difficulty to make observations with resonance bars, another idea is needed. And today, the existing detectors, they are laser interferometers. And so the principle is the following. So you have, of course, a beam splitter, and you have interferences. And if the gravitational wave hits the detector, then the lengths orthogonal to it change periodically, and this will change the interference pattern. So you will have here a laser, typically, and then you have here a beam splitter. That is, you have two, split into two, and there are mirrors. Here's a mirror, and here. So that they are brought together again and recombined and go here to the beam splitter, or that part, and here in the final detector. This is where you observe the interferences. Of course, if you want to see a change in length, a relative change in length, it would be advantageous to have here big, or as big as possible, arm lengths. Let me call them Y and Z, and let me call this the X direction. Now, in the detector, here we have constructive interferences and also destructive. So in the detector, so we have a constructive interference for delta L, which is Lz minus Ly, is n times the frequency, the wavelength, and we have destructive interference if delta L is n plus 1/2 lambda. No? So if you have the infalling gravitational wave, it periodically changes the arm length, and so it changes, because of these relations, the interference pattern that you see here. So you get from this change of interference pattern then information about the wavelength of the incoming wave. Because of that, the arm length should be as big as possible. So if you just do it in the laboratory, it is not so advantageous. So what has been done over actually collaborative work of many decades is to build detectors of several hundred meters, if not kilometers, arm lengths in a suitable environment. And so let me briefly review these. So we have the following existing detectors. So there is the big one in the United States called LIGO. So this stands for Laser Interferometer Gravitational Wave Observatory. And so there are two of them. The point is the effect is very small. So if you only one detector and you see a small effect, you can never be sure whether this is a real effect or just a perturbation. And if a train is in the passes by, then the amplitude caused by this train is much bigger than the effect. So you need to make coincidence measurements, otherwise you can forget. So in the US there were two such detectors in Hanford, Washington, State Washington, and in Livingston, Louisiana. And so the distance between the two is rather large, which is 3,000 kilometers, and the arm length of these laser interferometers is 4 kilometers. So they are really impressive labs, and the frequency range is between 50 hertz and 1.5 kilohertz. So, for example, the effect of the binary stars that I estimated earlier with 10 to the minus 5 hertz is definitely outside that regime. So you must have much shorter wavelengths for this to be seen. Now this is operating since 2002. You can find all the details easily on the the internet about the parameters and about the history. It has been upgraded, so-called advanced LIGO, in 2015, and then the first detection was made. There will be a final design this or the next year with increased sensitivity. Now there's also a detector in Germany called GEO 600, so near Hanover. So this is a joint project with the UK and Germany. This is of course US, and both of the two actually work together, and they are called the LIGO collaboration. So these two together are the LIGO collaboration, because here this arm length is only 600 meters, so it's much more difficult to see the effect here. But the point is that many of the technology has been developed here and tested here and then also put here. So in a sense these are complementary, they have complementary purpose, but they work together. And the signal, of course, the first signal that was seen actually arrived here was seen here, because you directly check by the computer about arriving signals. So there's another one, an independent one, Virgo, near Pisa. So this is a Italian-French collaboration. Has an arm length of 3 kilometers, so also very big. So, and also effects have been seen there. And there are also detectors in preparation. So there is LIGO India, which perhaps in the end of 2020s will operate, and also there is one in the planning stage and in Japan, and there are maybe also one in Australia, but that's not clear. Of course, it would be good to have them equally distributed around the Earth and also to cover the southern hemisphere, which so far is not the case, and also not with these two. because to see the direction really from the arriving waves, I mean, you need to have, I mean, big distances between the observer points to see the angles. Now, the first direct detection was very celebrated detection, was made on September the 14th, 2015, and the event is called GW, so this stands for gravitational wave 150914, so this stands for 14th of September 2015. And the Nobel Prize for this, and also then there were also then later this detections, was awarded in 2017 to 3 physicists. I mean, this is of course a big collaborations, but 3 physicists who were particularly responsible for the development were awarded the Nobel Prize of 2017. So this was Rainer Weiss, who had 1/2 of the prize, and Barry Barish and Kip Thorne, who shared the other half. And the Nobel Committee wrote it was for decisive contributions to the LIGO detector and the observation of gravitational waves. Yeah. Already in the second year there was in the first year there was a second event. So the second event, and because it was detected on the 26th of December, so it had then the number GW 151226. There are various other events now that have been found, and you can easily find an updated list on the internet. I should mention one here from 2017, 1708-17. I mean, it was found out that this one and also the first one arose from the coalescence of 2 black holes in cosmic distances. So this here, so this is from coalescing black holes. Whereas this one, this was very amazing. This was from a binary neutron star in spiral. From binary neutron star in spiral. And associated with this was also a gamma ray burst that was detected by the Fermi satellite short, I mean 1.7 seconds after this was detected. So they were really from the same event, and so you could see the same event, I mean the coalescence of this neutron star with a black hole or with another neutron star, that this same event was seen in the electromagnetic and in the gravitational regime. And the hope is, of course, for the future to see much more of those events and to study astrophysics not only in the electromagnetic but also in the gravitational wave regime. If you want to see more details or to read more details on this, there's a semi-pedagogical article that I can recommend, which you find 1608-01940. So it also contains a summary of the basic physics, I mean at least an observation at least, I mean in the year 2016. And because the objects, most of these objects are black holes or neutron stars, so we will come back to that in the summer term when we deal with black holes, and we will conclude then about really the metric of the black hole system that was indirectly detected here. But I should say that for the first event, so for GW, which is the 150914, that there were two black holes, so actually quite big black holes with large masses, and that the final mass, there was a coalescence of black holes, and the final mass, okay, was less than the sum of the two. So we had m final around 63 solar masses, or 63.1 solar masses. So, which means if you compare these numbers, that about 3 solar masses, or 3 mc squared, were radiated away in the form of gravitational waves. So 3 mc squared were radiated away in gravitational waves. And this would correspond to a luminosity that was of the order of 3 times 10 to the 49 watt, which corresponds to around 10 to the 23 solar luminosities in electromagnetic regime. Now this was this 10 to the, or 4 times 10 to the 33 ergs per second, or 10 to the 26 watt, which means that, I mean, this together corresponds to the electromagnetic luminosity of all the stars in the observed universe, also visible stars in the observed universe together. That big. No? So this corresponds to the electromagnetic luminosity of all visible stars in the universe. Not that big. Now, what about the future of this? By now, I mean, 6 years after that, we have quite a list of these events, and everything fits nicely with general relativity. So, as I said, for most of the time, the linearized approximation is valid, but not for the final fractions of a second. There you need a huge effort using supercomputers and the like. And but all the calculations done so far coincide very nicely with the predictions of Einstein's theory. So already various competitors of that theory were excluded by this data. Now the future, of course, we will have an upgrade and a continuation of the present detectors, and also these new ones, India, Japan, and maybe elsewhere. But there's also another route, and this goes to space, to interstellar space, or space outside the Earth, because there you have no perturbative effects from earthquakes and of seismic noise. And so the future will bring space missions, and there you can really, you have access to very small frequencies, very long wavelengths, in particular also possible effects from the early universe, where you have very long wave gravitational waves which cannot be seen by other means. And the present planned mission is so-called ELISA. So this stands for Laser Interferometer Space Antenna, and this is evolved LISA. There's a long history about that, which I will not present here. So there's a so-called LISA Pathfinder, so a prototype satellite that was launched in December, successfully launched in December 2015, so the same year where the first detection was made. And the final one is planned to operate, well, at least from the present prediction, 2034. So scheduled for 2034. And so what you have here, I mean, you have here the Sun and the Earth, and then you have 3 satellites that follow the Earth in its motion around the Sun here in this triangle. And they are such, I mean, this constructed such their location that really they stay together and follow the Earth. And so you again have then a very huge arm length here of course then thousands of kilometers. And if the wave hinges here, then you can see this in principle by the change also of the distances here, and you have of course high precision clocks and lasers here to check this. And the sensitivity is then in a interesting regime of very small frequencies between 0.03 millihertz and 1 hertz. And the amplitude is predicted to be seen for values of 10 to the minus 23 and bigger, of course. So, man, this would really be a very exciting mission, because you would then see, in principle, much, much more because of this increased sensitivity than you see on Earth. For example, as I mentioned already, primordial gravitational waves, or also gravitational waves that come from the coalescence of very big so-called supermassive black holes. Now, for that chapter here on gravitational waves, this small outlook is sufficient. You see, this is an exciting field, and many developments are expected to be achieved in the coming years and decades, and we can also expect then to learn much about the universe, also about its evolution from a totally different angle than before. Before, in astronomy, we mostly rely on electromagnetic radiation. Of course, a little bit of cosmic rays maybe, but mostly electromagnetic radiation. And gravitational waves can probe, I mean, many very different regime, also in time, as we will learn in cosmology in the next semester, that if you go back in time towards the Big Bang, I mean, the only possible observations you can make, I mean, relics from that period are gravitational waves. So thank you for today, and this concludes the gravitational waves chapter, and next time we will then derive the metric around the spherical symmetric body, which is the Schwarzschild metric. Until then.